You can do it later on, maybe after the class. Okay, try to find out, okay, what would be the advantages of using numerical methods. Yeah. Okay, now we come back to here. Okay, non-linear equations. So we've done the bisection, we've done the iterative method. And now today we're going to look at what is Newton method. Yeah. So go through quickly. Okay. Solving the non-linear equations, that is, you want to find what will be the x values. For example, if you can, as you can see from this screen, simple simple non-linear equations. Yeah. So this is the quadratic equations. So you want to find what is x values. It means that I want to solve it. Yeah, we call the x is a root. So when you put the x in the equations, it will return you 0. And in numerical methods, it will give you the approximated root. Yeah. So look at the bisections method. Okay, we have the intermediate value theorem. That we will use this theorem to test where would be the root of the functions. Yeah, by calculating what is the FA, what is FB. Yeah, so we'll select an interval. Yeah, then we put in the lower limit into the functions, upper limit into the functions, and if they have opposite sign, then we can say they exist at least one root. If they have the same sign, then there will be no conclusions because it can be a root in between or it can be no root in between. So we need to check it, yeah, by using graphical method, for example. Then bisection method, we can use a table. Yeah, to update the table, you have to find the midpoint, and you will get the intervals become smaller and smaller until the midpoint itself can be the estimated root of the nonlinear equations. Yeah, so that is the format of the table for solving the nonlinear equations using bisections. So for these bisections, yeah, you no need to do any differentiations like what fixed point iteration. Yeah, so what we need to do is we do the substitutions only. Yeah, so you had fx, you just substitute the values in and find the intervals, find the midpoint, update it, and look at what is the stopping criteria that you want, or if that is in the exam, then look at what is the stopping criteria given in the questions. Then you can check, okay, let's say you already have the fx that is very near to 0. Now, then you can just stop the iteration. Then you say this estimation is good enough, okay, for you to estimate the root of the functions. And if you can observe midpoint, yeah, it should be getting approach to a number that you want. And sometimes you will say we want to stop the iterations when it is correct to 3 decimal place, for example. Or you want to see, yeah, the interval of A and B, they are getting smaller and smaller until it is correct to 2 decimal places, for example, this one. Then at iteration 10, A and B, you can see these two numbers are very, very near. So that means within these two intervals, we will have the root of the functions. So we just take the midpoint, okay, as the estimated root. And so that is the concept of bisections. And then have the activity, okay, as a homework. And then we have the fixed point iterative method. Yeah. So for this one, maybe it converges faster. Yeah, but you have to find what is the gx. Yeah, gx, and you test on the gx by using the fixed point theorem. Differentiate the gx. Yeah, you get the g prime x and substitute the values within the interval that consists of root of the functions. So this one you have to use the intermediate value theorem also to estimate the interval if the interval not given. Yeah. So after that, if we found that it satisfied the convergence criteria, then we can proceed to the gx. So proceed to gx, you can use a calculator and you can just focus on these 2 columns. Yeah, and check the stopping criteria. Depends on what is the stopping criteria that you want to refer to. Then you can see also, yeah, we don't need to find the midpoint, but just a gx, substitute the values in the gx, and you will get the answer. Yeah. So the detailed concept of this fixed point iteration method, you can look at the textbook. Yeah. But actually for this class, okay, it will be more on how to use the methods, but not really to see or to prove where the equations or where the formula come from. Yeah, but you have to understand a little bit on the theory or the concept behind the methods. Then it will be more meaningful for you to continue with the solutions. And then after that, okay, we have the Newton-Raphson's. I think we haven't covered this, yeah, in last week lecture. Yeah? So now, Newton-Raphson. It is considered as an iterative method as well. Yeah, so then we have to run the iterative, repeat the steps until we get the solution that we want. So if you want to know, okay, how this Newton-Raphson work, also you can refer to the textbook. And actually this one is based on the concept of tangents. So meaning that you know, yeah, from the previous two methods, we need to always have the starting values. Yeah, so this one also, okay, we have the starting values, and we use the concept of tangents, okay, to find the iteration until it approach to the values that we want. Yeah, so example, here we start from x0, let's say, okay, for this example. The x1, okay, use this tangent. These are the color, yeah. And this is the x0, okay, initial values. Okay, then we go for this x1, iteration 1, iteration 2, iteration 3, and it is approached to the root that you want. So maybe 3 iteration, then you're able to get the answer. So actually this one, if you look at the concept, okay, maybe you have a quick look on that. And those who are interested to know how this Newton-Raphson method work. Yeah, this one. Yeah, it is about the tangent. Yeah, the tangent at the x0, f x0. Then you form the equation like this. Yeah, so this is the approximations or the formula. Yeah, based on the tangent line, starting from the x0, and then you want to find what is the x values where fx equals to 0 by using this formula. Yeah, so we will repeat the iterations until it meet the stopping criteria. Yeah, so that is the Newton method. Yeah, Newton method. So it will involve the derivative here. You can see there is a derivative in the formula. So for your informations, this formula not provided in the list of formula during your assessment, so you have to memorize it. Yeah. Okay, so now you can see, okay, how to find the x1. How to find the x1? Okay, we will use this formula. x0 minus fx0 divided by f prime x0. So you need to know how to differentiate this fx. Then only you put it into the formula, okay, as a denominator here, and fx, the original fx given, and then the starting values, then you find what is the x. Yeah, and this is only workable when we have the f prime x0 that is not equal to 0. For certain case, yeah, although we say that Newton method is a popular method because we just need a few iterations maybe for a simple example, and it converges very fast. But come to here, okay, although that is a good method, but it must have a limitations. Every method have their limitations and their advantages. Yeah. So one of the disadvantages of this Newton method is that the f prime, if the f prime x0 is equal to 0, then you cannot use this Newton method. Yeah, but the advantages of this Newton method is that it converges very fast. Okay, now we look at the general formula about this Newton-Raphson method. So this one I get the equations or the formula from other textbook. Yeah, it's not from our own textbook. So we can see if you want to find the xn, then we will use the previous x. Yeah, so let's say we always start from x dot. Yeah, so after you have the x naught, you want to find the x1. So it depends on the x naught, okay, minus f x naught divided by f prime x naught. Yeah, so find the values of these three and you get the answer. Okay, what is the answer? To find the x2, yeah, to find the x2, then you will use the x1. Okay, this is, sorry, this is a 1 here. Divided by f prime x1. To find the x3, after you got this answer, it will be the input for the x3. So this is similar to our fixed point method. But this fixed point, we use a 3x. This one, we use a formula. Yeah. So if you want to perform it manually, so this is the way you do it. And again, here, it will be different, a bit different compared to the formula that you can see from the textbook. Can make it larger. This is a formula that provided in the textbook. Yeah, we use I plus 1. This one I use I. But here in my notes, yeah, you can see that it's n and n minus 1. Actually, the concept is the same, but just the labeling. Yeah, if I change it to xi plus 1 equals to, so this will be xi minus fxi divided by f prime xi. Yeah, so for I equals to 0, 1, 2, 3, and 4. Yeah. So maybe some of you may ask, okay, why sometimes you use the iterations I is equals to 0, start from 0? Why some textbook they use the I that start from 1? Yeah. This is because of the notation that we use in the equations. Yeah. If you use this, then you will have to start from the n equals to 1. So to find the x1, okay, so that is equal to x naught minus f x naught divided by f prime x naught. But if we use I equals to 0 as a starting, then this one it will be x1 plus 0, 0 plus 1, that is 1, and this one is the x naught. Yeah? So these two actually they are the same formula, but just the labeling. Okay, any questions? Yeah, about the notations. Huh? It didn't say that, oh, I start the first one, n equal to, this one is I, n equals to 1, that's wrong, y that is start from 0, y start from 1, but sometimes because of the notations. Yeah. Okay, so now we go to the example. Yeah. So we try to see how we use the Newton-Raphson method, yeah, to solve the nonlinear equations. In other words, we find the root of the equations fx equal to 0. Yeah, solving the fx equal to 0 or find the root of the equations. Same thing. Yeah, this is just about solving the equations. Okay, so now again we have the fx equals to x power 3 plus x5, 5x minus 3. Okay, that is a polynomial functions, right? And you know you can use the calculator, but let's see okay how we use the Newton-Raphson method. But actually for numerical methods, yeah, why we learn this all and with the iterations? Yeah, sometimes when we have a very complicated fx with you, yeah, then we have to see, okay, whether the analytical solution will be much more easier, or maybe the numerical methods will help us better, okay, to find the solutions. Yeah. So for this one, okay, we will see what is the first step. Okay, what is first step that you need to do? Okay, let's look at the questions. Okay, starting point given, approximate the root correct to 4 decimal places. Yeah, 4 decimal places. That means when you run the iteration, it is already correct to 4 decimal places. The f remain unchanged, then you can just stop. Yeah, we don't have the stopping criteria, but actually you know different stopping criteria. For example, if we didn't have this correct to 4 decimal places, then you may have the stopping criteria given to you. Fx prime in the modulus is approximately equal to 0. Or we can say x, okay, this one we use n, yeah? So n minus 1, okay? Then, wait, wrong already. S is missing, n minus 1, yeah? So that is less than epsilon, yeah? Epsilon, yeah? Or we can say fx star, yeah? Less than epsilon as well. Yeah, something like this. Okay, we can use different stopping criteria, okay, to judge whether that is the appropriate answer that you want to see. Yeah, if you want to have a very accurate one, yeah, then maybe you have to set a very small epsilon, 0.00001, or maybe you say I just want to know roughly, okay, where is the x values. They just correct to 1 decimal place that's okay for you, then maybe you just set it as 0.05. Yeah, so it depends. But anyway, okay, for Newton represents, normally we can see the epsilon set in the question, it will be very, very small. Example, 0.00001 or 0.0005, yeah, something like this. Because this Newton method always converge very fast. But I wouldn't say it happens to all the examples, all the equations. But most of the time, yes. Yeah, but not guarantee for all the problem. Yeah, sometimes maybe for certain cases or no, for certain nonlinear equations, it's not suitable, okay, to use Newton represents, for example. Yeah, then we have to select another numerical methods. Yeah. So now let's see. Okay, this is a simple example, and we know that Newton method, yeah, the formula to find the x. Okay, this one you use n. Okay, then might use n. Or x1, yeah, to find x1, it is equals to x naught, yeah, minus f x naught divided by f prime x naught. So look at the formula that you have here, the first steps. X naught, it is given, okay, no problem. F x naught, no problem also. You can just find what is the f x naught, okay, that is equal to 5. Okay, so find out what is f5. But how about f prime? Yeah, in this question, it do not give you what is f prime. So you need to know how to differentiate it. Yeah, so differentiate the fx. So x power 3, so it become here, after you differentiate it, it is 3x squared. Differentiate the 5x, you have the 5. Differentiate the 3, you have the 0. So this is the f prime. Just substitute what is the f prime, okay, x naught 0.5 into the function. So you have 3, 0.5 square plus 5. So we have no problem, okay, to find these three values. Then means that you are able to find the x1. So this is how we do it. Yeah. So this is substitutions, x naught. This is substitutions for the f x naught. This one is the f prime x naught. Yeah. So we got the first x values. So this is the detailed steps. Yeah. But anyway, if you already understand how this formula can be used, how is the procedures, then you can just use calculator. Yeah. So look at the next page. Yeah. This is a way we compile all the solutions. Yeah. Actually, this is not really important. This is also not really important. You can focus on this and also checking the stopping criteria. Just now we start from 0.5. Yeah. You can set the formula in your calculator. Yeah. This one. Make it general. Yeah, make it general. So have the x minus f x naught divided by f prime x naught. Yeah. So you repeat the steps by taking this as the starting values equals to 0.5 equals to the answer E will be the input for the next iterations, and this answer E will be the input for the next iteration, and so on. Remember, okay, the fixed point iterations, we have the gx with us. Yeah, and you can find these steps, okay, how to use a calculator, either from this textbook, yeah, this textbook. Now we have the guide, you know, how to use the calculator, or you can look at the e-learning. Yeah, the e-learning we have the videos, yeah, the videos provided under week 1. Use calculator for iterative method. Okay, there are two models, right, of the calculator you can refer to. But if you have a different model, maybe you can explore yourself. The concept is the same. Yeah. So set the formula in the calculator and you're able to perform the iterations faster. Yeah. So observe the answer that you obtain in this table. That's very important. Yeah. Have to make sure that this number converge. Yeah. If let's say, okay, you use the wrong formula, for example, what I can see always is that this is actually minus, but because of formula not provided, or maybe there's a careless, okay, you put a plus here, then in these iterations, you can see they are something weird or something, no, that the changes of the number is not consistent. Converge, right? Suddenly it's a very big number, then it become a negative number, then it become a small number again, then become a large number again. So it won't be like this. So that means diverge. If diverge, then you have to double check on the formula that you set in your calculator. Yeah. Then if you're able to set the correct formula in your calculator, substitute the correct values, and these all symbols that are correct, because sometimes when you convert these equations into the calculator, maybe the plus minus sign wrong already, also you can't get the answer. So check everything that is correct using your calculator, then only you proceed. Okay, substitute the x naught into the formula, equals to answer, equals to answer, equal to answer, equal to answer. Within a few seconds, you will complete this table. And you can see here, the number here remain unchanged. So in these notes, you can see normally we have more iterations. Yeah, if you can see, because you want to observe. Yeah, if we continue with the iteration, what will happen? Although sometimes, okay, you already familiar with that, then we will say that it is already correct to 4 decimal place, right? This one, you round it, it will be 0.5641. Then you say, oh, I want to stop at 3. That is fine. Yeah, because if you use 4 decimal places, the difference of x2 and x3, they are actually 0. Yeah, then you no need to continue. But you want to see what will happen if you still continue. The number will be still remain the same until the iteration 5. Yeah. So although I say this is not important, yeah, but if you have time and you want to observe what happened to the fx, yeah, starting with the 0.5, you get these values. And then you know that this should be not a good answer, yeah, because x, if you say x is a solution for f(x) of 0, so that means when you substitute the x into the functions, you will get approximately equal to 0. So this is still far away from 0. Yeah. So when we come to this answer, you substitute this x1 into the fx. Yeah. So it becomes a smaller values. So luckily you know, yeah, that is the correct directions, or that is a correct way, yeah, for you to proceed. So this one getting smaller, and you proceed again, get this x1 as an input to find the x2. Yeah, use this using calculator. Okay, manual calculations may be taking time. Yeah, and it will create more careless mistake. Yeah, just set it properly once in your calculator or formula correct, then you run the iterations using your calculator. Now, so here you have the x2, okay, equal to this number. You substitute back to the fx, it becomes a very, very small value. Yeah, this one is 0.00006. 0, 1, 2, 3, 4, 5, 6, 2 something. Yeah, very small values. If you thought that, well, that is good enough, yeah, for you to say that this is the answer, then you will just stop at these iterations, because this fx is already approximately equal to 0. Maybe I write down f 0.5641. Yeah, is equals to this number, very small. Yeah, approximately equal to 0. Then you can stop at iteration 2. Or else you still want to continue, no problem. You can see even smaller. Yeah, you can see how many 12, 0, yeah, 0.00012, then 2141. Yeah, a very small values. And you continue, yeah. So this is even very accurate, yeah, compared to the actual solution. This one you can get a 0. Yeah, but we don't know what is the actual solutions yet, right? Because we say we just estimate it using the numerical methods. But you want to check what is actual solutions, you can just use a calculator actually. Yeah. The calculator can simply check the answer for you, especially that is just a third degree polynomial. Yeah, you put in the coefficient in and you see one of the answer, it should be this. Yeah. Okay, now back to here. Yeah, this is not compulsory. This column is not compulsory, but it just help you to do the checking, yeah, double checking on whether this fx is approaching to 0, where is this x is getting nearer and nearer to the answer. Yeah, and f prime also the same concept. Yeah, it converges to the number, so it's just an optional column for you. Normally we won't check it. Yeah, but we will have this column when we have the stopping criteria f prime x naught in the modulus smaller than epsilon. Then we have this column, but you won't complete the whole column. Maybe until iteration here, you found that they are getting nearer and nearer, and then you can start to check it. You don't need to check from the starting from the iteration 0. Yeah, but if you have time, you can do that. Okay, why I say that? Yeah, why I say that? Because normally the nature of these examinations, especially final exam, there are so many formula that will be tested. Okay, maybe I show you the list of formula. Numerical methods, yeah. Okay, the S methods, there are many methods. Okay, show you here. Yeah, this is basically the list of formula that you can see during the final exam. Yeah, so the first formula given is about Thomas algorithm. So it means that in chapter 1, yeah, in chapter 1, you have the bisection, you have the IVT, you have the Newton. They are not included into this list. Yeah, we only give you the formula that is more complicated. Yeah, so these are the formulas. Yeah, so 23 of them, and even you have a sub formula in between. Yeah, so it means that for these subjects, okay, there are so many formula that you have to know how to use it. Yeah, and then this syllabus also cover many numerical methods. So when come to the final exam, yeah, so imagine how many methods you have to know, and it is only 2 hours and 45 minutes. So you have to complete all the questions, the 4 questions, the long questions. So sometimes I would say, you can try to skip some calculations that you think that is not necessary. Just focus on the main one. Yeah, just like this. You know that you can check it using the fx, f prime x, no, to double confirm that they are correct. But sometimes, if you already understand, no, but understand well how these methods work, then you can skip some step. For example, this one no need to see because that is definitely much more larger compared to epsilon. Then you can start to check it when you found that these x values they are getting nearer and nearer and approach to a number. Then you can just start to check on. You can start to check on a few of the fx that is towards the end of the calculations. Yeah, that is fine. That's fine for me. Yeah, unless we have a lot of time. Yeah, just focus on these interruptions. You want to do further studies or further investigations about this method, then you can have both or 3 or 4 columns. Yeah, to see what are the changes of the x values, fx values, f prime values. Okay, so now at iteration 3, now you can see the explanation here. At iteration 3, this is iteration 3. Fx equal to 0 is up to 10 decimal places. Yeah, we want to consider more. Yeah, but of course in your textbook, in the exam, we won't ask you to consider until 10 decimal places, but this note is just for you to understand better. Okay, actually we can calculate up to 10 decimal or more than that, yeah, decimal place. So here, okay, this indicates that, okay, these will be the solutions. It's a good approximations to the root of the equations of these polynomial functions. Yeah, but you just want to see it is until 4 decimal places. Yeah, then we can conclude that the root of the function is 0.5641. Yeah, so just round up. Yeah, 4 decimal places. Any questions so far? No question? You have question, you can put in the chat box or you can on your mic to ask. Yeah. Okay, if no questions, then we proceed to the example in the textbook. Yeah. So in this textbook, okay, we have this example. Yeah. E minus x equals 0, same like what we discussed last week. Okay, we use bisection method to solve these equations, and we use a fixed point iterations method with 2gx, okay, to solve it. Now we will see how to solve it. The same, yeah, exactly the same equations using Newton method. Okay? So now, first of all, Newton method, you know what you need to have is that x naught, and then substitute the x naught into the fx, and you need to have the f prime x naught, yeah, to get the x1. After I have the x1 with the input, yeah, to find the x2. So to find the x2, we already had the x1 with you from the previous calculations, and put in the x1 here, put in the x1 here. So this is an iteration process. Yeah, but we don't do it manually. Yeah, don't do it manually. We just use calculator. Okay, so see how we do it. Okay, we let the fx equals to e minus x minus x. So find the f prime. So here it will test you, yeah, how to do the differentiations for the exponential functions. Yeah, and yeah, if you have the problem with the differentiations example, yeah, so what should you do? You suddenly forget how to differentiate the ex. You forget how to differentiate the sine, the cos, the minus or without the minus. Yeah. So what should you do? You don't have the table provided to you in the list. Okay, differentiate of sine, what you have, differentiate of cos, what you have, right? You can actually use a calculator. Yeah. You have the scientific calculator, you can do the differentiations. Okay. And then with the x, what is the x? So this one you have to substitute the values in. Yeah. So if let's say you start from x naught equals to 0, then start from x naught equals to 0. Yeah, use a calculator to calculate. Just in case you don't know how to differentiate. Yeah, that is another way. Okay. But normally the differentiations it should be no problem. The most difficult one I think is the trigonometry. The rest of it, polynomial, I think no problem. Exponential also no problem. Yeah, a square root, cube root, and so on. It should be no problem. But just in case, you forget how to do the differentiations, you can just use a calculator. Yeah, because we will test more on how you use the numerical methods and substitute the correct answer in. Yeah. Okay, now differentiate this f, we get the f prime. Yeah, differentiate this, we get this. Differentiate x, -1. Yeah, because of the minus sign here. Yeah. Then now we put them into the formula. Yeah, put them into the formula. This is the xi still the same. x1, x2, x3, x4 depends on how many iterations you need. Fx, okay, this is fx. Yeah, after you differentiate the f, then you get the f prime. Put the f prime here. Yeah, stop the iterations when the values of the x compared to the previous x, they are smaller than, okay, the difference smaller than epsilon. Okay, so epsilon, you set it as 0.000. Okay, set this in the calculator. So how to do it? Yeah, you can see the steps on using calculator. Set this one in the calculator and calculate what is x1 equals to answer equals to answer equal to answer. Within 2 seconds, you get the answer. You stop here. Why you stop here? When you try to observe the changes of the x1, x2, x3, and the difference, yeah, the difference for x compared to the previous x, it is smaller than 0.005, then we stop. For this one, what is the difference? The difference is, of course, you see, very obvious, it will be greater than that. But come to these iterations, the difference is 0.0001. Yeah, regardless that is positive or negative, I mean the difference. Yeah, as long as in the absolute, yeah, you can see the modulus. Yeah, that is smaller than epsilon, then we stop. So we stop at iteration 3. Yeah. So we can check the answer after obtain here. You check the answer, you substitute it back to the fx, and it is equals to 0.001, approximately equal to 0. So that is the answer. Okay. So any question? No question, we go for the exercise, yeah? Okay, so class, have we discussed about question number 2? I think 1, we have done it. Number 2 is about the fixed point iteration method. This one is about Newton-Raphson. The fixed point, have we done it? This one? Have we discussed it? Yes, huh? Okay, now we will go to the Newton-Raphsons, yeah? So same, okay, we look at the partial questions, yeah? This is one of the partial questions. Now have a look on this, get an idea how to solve it. Maybe the certain partial questions you can see is not that straightforward. Okay, as you can see from the example given, but you have to do something. Okay, do the proving or show some, how we get, the formula from the Newton-Raphsons to do the approximations. So have a look on this. Okay, now you may ask, where's the fx? Yeah, where's fx? If the fx equal to 0, then only you can proceed to the f prime. But this seems like only the equation given, right? So you have to form the equations and then we find the differentiations. Yeah. So you want to estimate, okay, what is the t? T equals to cube root of 18. But actually for this question, you can just use a calculator to find the answer directly without using the Newton methods. But for certain case, yeah, if you want to estimate it, maybe not cube root, maybe the higher numbers here, then maybe you can use this way, yeah, to do it. In calculator, okay, you cannot do it. Okay, example, yeah. Then you want to use a manual way or the iteration way, iteration process to estimate the root. Yeah, that is okay. For many real case, yeah, we don't have actually this fx given to you directly, right? So you have to think about how to get it. Okay, you learn about the mathematical modeling, maybe. Then you have to know how to form this fx based on the data set that you have. Whether the nature of data, there is a quadratic, okay, or there is a polynomial, or there is the exponential form, and so on. Yeah. So these equations, maybe you can learn it in other chapters and maybe from the previous subjects, how to form it. But this one, okay, back to here, we don't have the function with you, but there is no problem for you to form the equations. So given this is the informations, you want to convert it or you want to transform it into the form of equations. So you put the power for both of them. So 3t power 3 equals to 18. Yeah. So t power 3 minus 18 equal to 0. So here you have ft equals to t cubed minus 18. So you want to see what will be the t, yeah, when the fx equal to 0. So you want to solve these nonlinear equations. Yeah. So once you have the ft, then it will be same like what we have in the textbook. Yeah. So just calculate what is ft. Yeah, this is the ft. So I have the ft with you, have the f prime t with you. Is the t naught given? Yes, this is the t naught. And now you can form the equations using the Newton-Raphson formula. So now you want to find the ti plus 1. So ti plus 1. Okay, so we start from the original formula, ti plus 1. Yeah. To find the ti plus 1, we need the ti. Okay, the t in the previous iterations minus f f fti divided by f prime ti. Yeah, this is a Newton-Raphson formula. That's how we use the fx. Now it's t because now the unknown is t. Yeah. So now you can proceed. Yeah. Okay. Ti plus 1 equals to ft. Want to find the general form. So this is the ft. So t cubed minus 18 in the bracket. This one is 3t squared. Okay, simplify it. See whether you can get this equation or not. Okay, so let's try to do it now. See whether you can prove that this ti plus 1 can be also written as 2 over 3 ti plus 6 over ti squared. Okay, so can get the same. Should be the same, right? Then just simplify it. Okay, so show that, okay, it can be written in this way. Now, this question is a bit special compared to the example that we discussed just now. Just give it fx and then differentiate it, put it in the formula, then you can just proceed. But for this one, you have to prove it. But just in case you don't know, you forgot, you panic, okay, you don't know how to prove it, no problem, yeah. You can just proceed with this formula, okay, in the iterations. Yeah, so everyone got it. 2 over 3 ti plus 6 over ti squared. Yeah, so we got it, then we can just proceed. Yeah, proceed to the iterations. Yeah, now you draw the table. Okay, iterations. I build a table. I build in the same page so we can see. Normally, our example won't spend many iterations for Newton-Raphson's. Yeah. Okay. So now we have the table, and we try to set it. I plus 1, I plus 1. So you can start from I equal to 0. Yeah. So this is T I. Yeah, Ti. And then the stopping criteria is already given. So T I minus t, I minus 1 in the modulus smaller than epsilon. This is epsilon. Yeah. So what's the t naught given? T naught is 5. Yeah, so I put in 5. Okay, as a starting values. And now, after you prove it, you can't get this. Okay, double check again. Okay, what's wrong? Yeah, with the proving. So yeah, everything done. Yeah, then you can just proceed with this formula. You can set this formula, yeah, in the calculator, 2 over 3 t plus, you don't have t in the calculator, can you set x, yeah, plus 6 over x square, yeah, in the calculator. You press equals to, put in the 5 and see what you get. Yeah, in the first iterations, when the t naught equals to 0, t naught equals to 5, you will get the t1, yeah, this is t1, 3.5733. You got the same? Okay. So if you check, okay, the difference of x0 and x1, okay, there is a huge difference compared to the epsilon. So we will proceed. Equals to, your calculator equals to, put in this answer and fill up the next answer. Then you try to see these two. Still, okay, there is a difference. Okay, then we proceed. Equals to, calculator, okay, don't clear the formula. Equals to the answer just now. Then you can try to see here whether this number is getting nearer and nearer to the previous one. Yes, right? And then iteration 4 equals to, yeah. But it's still, yeah, the difference is still larger than the epsilon. Never mind, we continue. Now, until here, you can see T5 minus T4. This one minus this one. You get a minus 0.0002. But in the modulus, right? Modulus. So you can say that is smaller than epsilon because 0.0002, yeah, that is smaller than epsilon. Then we stop at these iterations. Yeah. So you can see here, the answer is a little bit blank, but if you want to complete the whole column, that is fine. Yeah. So you check what's the difference, what's the difference, what's the difference until these steps. Now, then you can find that is less than. Because we're doing manual calculations and then we are human, right? A human, we are able to judge, okay, by just looking at it. Then no, okay, we can skip this step because not yet. Yeah. The difference is still quite large compared to the epsilon given. But when you do the setting in the computer, let's say you want to program it, you want to use Python, you want to use MATLAB, you want to use C programming, to solve this kind of problem. Then of course the computer will check one by one of larger than, okay, continue, larger than, continue, larger than, continue until smaller than the epsilon that you set for the you set in the coding. Yeah, then it will stop here. Okay, so what you can say, okay, don't leave your answer like this in the table without saying that which one is the root. Yeah, so there are so many numbers here, which one is the root? Okay, t star is the root of the functions, or maybe you say for this example, okay, cube root of 18 is approximately equals to 2.6207. So if you have a calculator with you, yeah, calculator, take out the calculator, you calculate this and double check with this. Are they similar? Is it correct to 4 decimal place if you use a calculator? Yeah, if I use my calculator, Yeah, that is 2.62074139 So that is good enough. Yeah, that is good enough for you to use the Newton-Raphson method to approximate the solutions. So maybe calculator give you more decimal place, but when come to the applications, is this 10 decimal place important for you in the measurement or in the calculations? Yeah, if not really important, I think 4 decimal place that is good enough. So sometimes it depends on um, the unit, yeah, of the variable, or maybe on how serious, you want it to be correct the 4 decimal places, for many, or you must get the very very near to the correct answer that is correct to 10 decimal place, then that's fine. Okay, you just ask the computer to do it. Okay, manually we just want to understand, okay, how to perform these Newton actions, that only we can program it. Yeah. Okay, so that is the answer for these questions. And this question is very similar to the one that we have in the activity. Yeah, so this will be another homework for you. Yeah. Okay. Any question until here? For Newton Raphson's. Okay, wait. Okay, this one is the one that we discussed. Yeah, just simple iterations. Just a few iterations, you got the answer. And sometimes you may also try to see, okay, if you didn't follow this t not equal to 5, you want to start with any value that you want. You can try to see how many iterations. You still can get it. Actually, this Newton-Raphson method is quite good in converging, in convergence. Maybe you can start from t not equal to 20. Maybe you need 2 more iterations, you get the answer. Maybe you want to start from t not equals to 10, and then you will see, yeah, you still can get the answer actually. Okay, guys, we will have a 5 minutes break. Okay, so after 5 minutes, then we will continue to the first subtopic of the chapter 2, yeah. Okay, 5 minutes break, yeah. Okay, class, come back, yeah. Okay, so I want to scan your attendance already, right? So I have 47 of you. 47 of you, but here in the list I have only 42. 5 is missing, yeah? Okay. So now we will continue, yeah, with the second chapters. That is about, sorry. This is about solving the system, yeah, solving the system. I will share it again. Now, you learned about solving the system of linear equations before, yeah, since your secondary school, you know, even the primary school now also they talk about the concept of this system of linear equations, right? So system of linear equations, try to recall what's that. Okay, you have ax1 plus bx2 equals to b1, ax2 plus something 1. A1, A2, yeah, something like this, plus B x2, this is 1, equals to B2, okay, in general. Two equations, two unknown, equation 1, equation 2. So you learned it before, yeah, how to solve the system of linear equations. You can do the substitutions, equation 1 minus equation 2, and so on, yeah. Then you solve it manually. And now you have a calculator with you, you just use the calculator to solve it. Okay, and even your calculator can solve until 4 equation for unknown. Yeah, but now you want to see how we use numerical methods to solve it. Yeah. Okay, so for this one, yeah, you can have the textbook, you can read through, yeah, the general form. Basically, it's not only 2 equation to unknown, maybe 4 equation for unknown, but we can have a very large system of linear equations. Yeah, but for our syllabus, normally we look at not two, look at least 3 to 4 non unknown and also the equations. Yeah, and then we will look at several methods on how to solve this system. Yeah, it's not only one method to solve the system of linear equations simultaneously, but we have more methods. And basically for these chapters, yeah, we will learn about the numerical methods. Yeah, different types of numerical methods. Yeah, to solve this kind of problem. Yeah. So now you see how many types. Yeah, if you look at this figure. In this figure, we basically want to show you in overall what will be covered in our chapter 2. Yeah, chapter 2 we talk about the linear system. 3 times 3, 4 times 5, 4 times 4 linear system. And then we have 3 types of numerical methods. First one is elimination method, followed by the LU method, followed by the iterative method. So under elimination method, we have 2 of them, Gauss eliminations and Gauss elimination with partial pivoting, that we will cover it today. Yeah. And tomorrow we will cover this Doolittle, Horosky, and see whether we have time to cover another one, Thomas method. Crowd method in our textbook, but we are not going to discuss it. Why? Because it's not important, yeah, but because of the concept is very similar to Doolittle. If you know how to do Doolittle, then no problem for you to go to the crowd. So we only focus on one. Yeah. And then we have the Jacobi, we have the Gauss-Seidel. Now, for this Thomas method, the formula will be provided. Yeah, formula will be provided in the list of formula. You have to know, yeah, this is Thomas. Thomas. You can find this Thomas formula in the list of formula. Yeah, have to know how to use it. Okay, come back to here. So chapter 1, no formula provided. Chapter 2, only one formula will be provided. So for the rest of it, you need to memorize the formula. Yeah, but this is a small formula. Okay, not as complicated as Thomas algorithm. Yeah. Okay, so this is the overview, yeah, of the chapter 2. Yeah, numerical methods in solving the linear system. Okay, so now we go back to this one. Go to the textbook. Okay. Okay, so in general, you know the system of linear equation can be written in this form and also can be written in the matrix form. Yeah. So in the matrix form, you have the AX equals to B. So solving the system means that you want to find what are the values for x1, x2, x3. If let's say you have 3 equations, 3 unknown, then we'll focus on this part. 3 equations, 3 unknown. So solving a system means that you want to find what is the x1, x2, and x3 one by one, so that these numbers satisfy all the conditions in these 3 equations. Yeah, so solving it simultaneously, get what is x1, x2, x3 if that is matrix 3 times 3 for the A. Yeah? So we have the basic, again, you learned about matrix before in EM1, EM2 as well. So you have the AX equal to 0 is homogeneous, but this is just to recall the concept of the matrix equations. But here, we not really look at the basic concept, but you focus more on the numerical methods, yeah, different types of numerical methods. But the concept, okay, the basic concept you still need to recall sometime, yeah, how to do the multiplications and so on. Okay, then we have this augmented matrix. We will use the vertical line to split the matrix A and B. Then only we run the Gauss-Jordan eliminations. Yeah. So Gauss-Jordan eliminations, you learned it before, that it will involve row operations. For these numerical methods, yeah, we will have the similar methods that we call it as Gauss eliminations, and also Gauss elimination with partial pivoting. Yeah, 2 of them. Then we'll see what are the difference. And then now, you know numerical methods will only give you the approximations. Yeah. So how about checking the performance of different methods? So when you solve the system, let's say, okay, x1, x2, x3, then how you judge, whether the answer provided by this numerical method is good enough for you to stop the iterations, or is good enough for you to do the approximations? Yeah. So normally we won't check it one by one, but yeah, we will check it one by one, but we will have a measures, a number to describe the accuracy of the output. Yeah. So that's why here we need to learn the norm. You have the 1 norm, you have the 2 norm, you have the infinity norm. So this all is just for us to do the checking. Yeah. Use a vector norm to check whether this answer is correct or not. Example, in numerical methods, okay, this one we get 0.999. And then 0.002. And x3 we get 0.998. Yeah, this is from numerical methods. And the actual solutions, okay, let's say actual solutions. We have the actual solution given to you. That is xy should be 1, x2 should be 1 also, and x3 it should be 1. But the difference here, yeah, what the difference? 0.001. Yeah, that is the difference for the x1. And this one 0.002. And this one 0.002. So we have 3 difference, yeah, from numerical methods, answer from numerical methods, actual solutions, we get the difference for x1. And you get the difference for the x2, get the difference for the x3. So how can we say, yeah, the accuracy, you just want to use one number. So let's say by looking or by calculating the difference. So we just total up the error. Yeah, the difference, or maybe the error, the actual solutions, and the one that you calculate using the numerical methods. So total up, so you get the 0.005. Then we say that this is the error, vector error. Or you want to use a Euclidean norm. Yeah. Then we will say, oh, we will use these equations to calculate the norm. Now, actually for here, okay, when we calculate the error, we only consider the absolute values. For example, this one, I consider the absolute values. This one minus this one, I got a positive. This one minus this one, I got a positive. Sorry, I got the negative actually. But in modulus, it is still 0.002. This one minus this one, yeah, no problem. So why we use a modulus? Because you just want to know the difference, regardless that is positive or negative. Yeah, so that's why we put a modulus. After that, okay, if you don't want to use this first norm, to measure the vector norm, then we can use a Euclidean norm. So each of them is square, square, square. Yeah, total up, find the square root. Or you want to use infinity norm. So what is infinity norm? Example, you have this one. So infinity norm, it will be max of 0.001 and minus 0.002, 0.002. What is the maximum difference? 0.002. So we only look at the maximum difference. If let's say the maximum difference that is smaller than the epsilon that you set, then you can just stop. Or maybe you say that this one is smaller than epsilon that you set, 0.01, and then you stop. Yeah, something like this. So this numerical methods also will involve the stopping criteria. When it comes to stopping criteria, we need to have the standard, yeah, or the rules for us to stop the iteration. So we can use this norm. Yeah, we calculate the difference between each of them. Then either see if we want to use a one norm or two norm, Euclidean norm, or sum of magnitude, or the infinity norm, yeah, to stop the criteria. So there are different types of them. So depends on which one, yeah, you want to use to stop the iterations. Okay, so that's just the idea. Yeah. So later on when we go for the example, then we will see in certain questions we will have this symbol. No, this line, this symbol, and X in between, and have the infinity. So when you look at this symbol, then you should know that is infinity norm. Yeah. Okay, now go to the elimination method. Elimination method. So same with the Gauss-Jordan eliminations, we have this row interchange. Okay, row interchange. We have the row scaling. We have the row replacement. Yeah, to find the new row. Yeah, based on the row reductions, then we can see okay how we find the alpha and find the new row. Yeah. Now, Gauss elimination method, you try to recall. Normally, we will start from the augmented matrix. Yeah, with n equations, n unknown, two equation, two unknown, three equation, three unknown, and so on. For manual calculation in our course, normally it will be 3 to 4 equations and unknown only. Yeah, but for more equations, for example, 10 equation, 10 unknown, and so on, yeah, then you can use the numerical methods to solve it. Of course, you have to use a computer to solve it. Yeah. Okay, now, what is the purpose we do the Gauss eliminations? You want to find the unknown. Yeah. So we will first make it into the augmented matrix, and then reduce the augmented matrix into the upper triangular form. So after it becomes the upper triangular form, then you can use the backward substitution to solve it. Yeah. Try to look at this example. Yeah? So in this example, yeah, solve the following system of linear equations using Gauss eliminations. So 3 equations, 3 unknown. Instruction given, denote that this approximation, the solutions can find the solution of the x. It means that this x hat is the x1, x2, x3 is a vector. Then we have this calculate the residual errors. How to calculate these errors? Okay, the magnitude. and calculate the error vector as well. Later we'll see the example. Yeah, when given the actual solutions is 1 minus 1 and 1. So how you compare it with the solutions that you find by using the Gauss eliminations. Now, we will go through, yeah. First of all, from this system, you will transform it into the matrix form. After that, into the arithmetic form. Okay, this is the arithmetic form, and where from this Gauss eliminations, yeah, we have the fixed procedure for it. It's not like the Gauss Jordan. You can first do the row interchange, or you want to divide the first row with the private element to make this become 1 and so on. No, yeah, we will just follow the procedure. The first procedure is that for Gauss elimination method, you look at this first column, because now we want to make this to be 0, this to be 0, this to be 0. So we do it step by step so that you're able to get the upper triangular matrix where these three number it should be 0. Now how to do it? So first we calculate the M21 and also M31. What's the purpose to calculate this? Because you want to perform these operations so that these two become 0. Yeah. So how to make it 0? You find the M1. M1 is A21, okay, divided by A11. A21 divided by A11. So we get the M21, that is 0.5896. So when we substitute it here, minus 0.5896 multiply with the R1 plus the R2, then you will get this approximately equal to 0. Then we will perform these operations to the next column. So since you already have this M21, so minus M21 multiply with the R1 plus the R2, then you will get a new R2. Okay, so repeat these steps until the whole row 2 can be updated. Yeah, and next, yeah, how to reduce this to be 0? The same, we calculate the M31. M31 equals to the A31 divided by A11. So we get this 1 point something. Then we put it into the operations. Yeah, so this should be reduced to be 0. Yeah. Then for the same operation, we perform it for the whole row 3. Yeah. So we will see what happened. Yeah, these are the step by step. Yeah, step by steps. Okay, this one you don't need to consider. Yeah, no need to consider. You only consider our mathematics and also the operation. Okay, so these operations will return us now. This should be 0. The values below the private element should be 0, and this is the new row 2. Then new row 3 also. Okay, now we obtain this. Okay, so what's the next step? The next step is we want to make it to be 0 so that we can obtain the upper triangular matrix. Yeah, so how to make this become 0? So same thing. Okay, we use the formula M32. Yeah, this is M32 equals to, now these values divided the value above it as a pivot element. Here we won't touch on the R1. This will be the pivot row. And these second values will be the pivot element. Yeah, so A32 divided by A22, you get the 25 something. Then we put it into these operations. Now the operation is fixed, just the number is changing. Okay, number of M31, M32 is changing. Number for R2, R3, they are changing. Okay? So these are the manual calculations. So once you have this here, that is M32, you put it here M32, 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 M32. Yeah, you repeat it for 1, 2, 3. 3 steps actually. This one no need. Okay. Okay, this one is for this one. 1, 2, 3. 1, 2, 3. Okay, this one no need. This one just other checking. Yeah, no need. So we only focus on these 3. By using these operations, then we get a new row. So 0, put it here. 94 something, and put it here. 94 something, you put it here. So now we achieve our target, that is to make this augmented matrix, reduce it to be the upper triangular matrix. This is upper triangular matrix. Once the matrix is in this form, then you know the next step is that we will do the substitutions. Yeah. So first of all, we are able to find the x3. Yeah, based on these equations, we are able to find x3. From the x3, we find the x2. From the x3 and x3, we find the x1. This is about the backward substitutions. Yeah, Gauss-Jordan, not Gauss eliminations method. So probably here you can check on the actual solution given. Yeah, it should be 1, -1, and 1. Actually, after the long steps, you want to check the answer is correct or not, you can substitute the x1, x2, x3 back to the equations and see whether there is approximately equals to the right-hand side values. Now, how to check the residual errors? This is one of the way we check the residual errors. That if we use the right-hand side values minus the a multiplied with the answer that you just obtained. If they are near, yeah, then that means there is a solutions. Because you want to find what is the x1, x2, x3 values. When you put it into the equations, it is equal to the right-hand side values. So now you get the residual vectors. It's quite small, right? It should be a small values, okay, or small values for all the x1, x2, x3. Yeah, and then now we wouldn't want to have like three values. Yeah, you just want to have the one, you want to have only one measurement. So we can use the residual vectors. Yeah, we can use the two norm, yeah, to find what is the difference. So square all the values, total up, square root, you get 0.025. Yeah, so on one of the way to check the accuracy. Or you can use the error vector. Error vector is that we use the actual solutions minus the one that you obtain. Then you use the two norm formula also to find what is the error. Yeah. So if let's say this actual solution not given, then you can just proceed to the residual error vectors. Yeah. But this is given, so we can do both. But in fact, in these questions, yeah, the instruction is asking us to do both. So follow the instructions. Normally in the assessment, we only ask you to do one comparison using one way. Yeah, unless there are 2, 3 methods, then maybe you can compare which method is better. Yeah. So either R hat or either E hat. Yeah. So we calculate the error vector, then the magnitude, yeah, and then calculate the residual vector, and then also their magnitude. So this is the way we compare it with the right-hand side values and also the actual solutions. Okay. So now we go for the Gauss emissions with partial pivoting. Yeah. So with partial pivoting, similar to Gauss emissions, but what are the difference? Yeah. So you can see the procedure. Yeah, we have the extra procedures is to check the pivot row containing the largest absolute values as a pivot element. Before this, we just continue. Whatever the matrix that given to us, then you start to calculate what is M21, M31, reduce it into the 0 for the first row, and the first column, except the pivot element or the element below the pivot element, reduce it to be 0, and then so on. But here, Gauss emission with partial pivoting, then you have to check on whether the pivot element, yeah, is the largest compared to its column. If that is not the largest, then you have to rearrange the equations. So this process, we call it as partial pivoting. Yeah. So now we look at the same system again. That's how we solve it using the Gauss emissions. But now we use the Gauss emissions with partial pivoting. Exactly the same instructions given to you. Now let's see what are the procedures that is different from the previous one. Now, first of all, from the system of linear equations, now we transform it into the matrix form and transform it into the augmented form. This one only. Transform it into the augmented form. Then you try to observe. Okay, this one normally located here, we call it as pivot element because we will use it to reduce the values below it to be 0. But for partial pivoting, yeah, you have to make sure that this element will be the largest absolute value. If that is a negative, so you take the absolute values. Yeah. So this one, yeah, you can see this is smaller than here. 2.68 is larger than 2.51. Now, you have to perform the row interchange. That means the procedure partial pivoting. You have to do the row interchange. You interchange the whole row. Not only the numbers, yeah? You have to interchange the whole row. So the whole row 3 interchange with the row 1. Now, you will see what happened here. Okay, so now this row is located as at the top. Yeah, become the row 1. So check again. Yes, this is the largest absolute values compared to the values below it. Then only we perform the Gauss eliminations. So same procedures, we calculate the M21, calculate M31, yeah. Then we have these operations and reduce this to be 0. Yeah, this one update it, update it, update it. You got all the values here. Yeah, these all values. And we'll put it into the new row. This is a new row 2. Yeah, this is a new row 2. And same, yeah, after we calculate the M31 using the A31 divided by the pivot element A11, you get this 0.9 something. And perform the operations, you get the new R3. Yeah, so this is a step-by-step how to do it. But actually, you can set this procedure in your calculator. This is the constant. Yeah, just put in what is R1, R3, you get the new R3. R1, R3, you get the new R3. R1, R3, you get the new R3. Yeah, so come to these steps. We know that the next step is to reduce it to be 0. Yeah, but before we calculate the M32, okay, have to double check. Now the pivot element should be located here. And compare it with the element below it. Which one is the absolute largest? Of course, it's this one. So we need to do the row interchange. R2 interchange with the R3. Okay, so now you get a new matrix. After the interchange, now this pivot element is larger. The absolute values, absolute values is larger, largest absolute values, yeah, compared to the values below it. Then now proceed, same thing, calculate what is the M32. Take this A32 divided by A22. Yeah. Then you get these values and put it into the operations and update the row 3. This is a new row 3. This should be 0 or approximately equal to 0, but correct to 4 decimal place, you should put just 0. Okay, then put in this one here, this one here. Yeah, this one on here. In the new textbook, yeah, you can see that is same procedure as well. Okay, after you become the upper triangular matrix, use the backward substitutions to find the answer. Now, this is the answer. And try to compare it with the Gauss function without partial pivoting, yeah? Okay, this one with partial pivoting. Okay, this is partial pivoting. Just now without, yeah, this one, yeah. Yeah, 0.9990 minus 0.998311, yeah. And then we use the residual vectors, magnitude 0.005, 0.0025, this error is 0.0020. We compare it with the partial pivoting, where we do the row interchange based on the partial pivoting. Is it more accurate? Okay, let's see. Yeah, it's more accurate, very obvious, right? And when we calculate the error, this one we got 0.002 something, yeah, 2025. But this one, the error is only 0.001. This one also 0.001. So we compare two examples, yeah. Example 2, Gauss mission with partial pivoting, yeah, it is more accurate compared to the X hat, well, with the actual solutions. Okay, so this is why the theory behind is that, yeah, for Gauss simulations method, numerical methods, when we're calculating the m, yeah, the multiplus, okay, this one. If without the partial pivoting, you can see here these values and these values. M3, M32, this is still okay, but because 1.48 is smaller than the pivot element. But when it comes to here, if you do not do the row interchange, this is larger, this is smaller. So what is the M31? 1 point something, of course, because this value is larger than these values. Yeah, 2.68 divided by 2.51. Yeah, 1 point something. But you go to partial pivoting. After the row interchange, this M31, 0 point something. Yeah, smaller than. And also look at M32. Now M32, you can see these values is much more larger compared to the pivot element. So here you can see when we calculate the M32, this multiples is very large. Yeah, but with partial pivoting, okay, we need to do the row interchange. Then let's see what is M32 here. M32. This one 25 something, no? 25 point something. This one 0.5 something. Yeah, just because of row interchange based on the partial pivoting. Yeah, so we get the different accuracy. Why? Because the concept is very simple. When you have the smaller values, then the error, yeah, that you obtain, it becomes smaller. With the larger values, so during the operations, you will give it a little bit larger errors. And so that's why we need to do the row interchange to guarantee that we have a better approximations using numerical methods. Okay. Now, so far, any questions? Where's my chat box? If you have questions, you can ask here. No, no questions. So far, so good. I'm not sure whether online class, no. Online class, I can't really monitor the progress of hands-on sections. Yeah, normally if there is a physical class, you will have a better discussions because I can go to you all. Yeah, you have questions, you can just ask during the exercise slot. Yeah, but here I can't really see, no, whether you can follow or not. Yeah, but anyway, yeah, just get the concept, and we will still go for the hands-on. But due to the limited time, now it's already 9:42. It be a long solution, so I think 20 minutes is not enough to cover these topics, to cover these hands-on sections. So maybe this one I leave it to tomorrow. Yeah. But the question is already in the e-learning. So if you want to try to start, you can start it. So the question given like this: solve the system of linear equations using the Gauss emissions, with partial pivoting. Calculate the show your calculation in 4 decimal place. Actually, for this kind of questions, yeah, although you use a numerical methods to approximate the solutions, but sometimes after the long step, you want to see whether your answer is correct or not. You just use calculator to check it. Calculator will give you the accurate answer. But here you just learn the concept. Maybe you ask, why calculator can do that? We still need to use the long step to do that. Yeah, because for certain system, yeah, for certain system where your calculator cannot solve it, and manual calculation also quite difficult. So you can use the techniques you learn here and you program it. Use the coding, programming coding, and then you solve it. Yeah, so that is the basic idea lah. Okay, for you all on sometimes why the example given in the class is so simple. Now you still ask us to use the complicated methods, techniques. But anyway, numerical methods, basically when you choose it, choose them to solve the certain problem, means that the certain problem, maybe you have a very complicated functions. no, then numerical method will be a good choice. Yeah, so this one we'll discuss it tomorrow. Yeah. Any questions before we end our class? Tomorrow our class will be at 11, yeah? 11. You can find the link from the e-learning. Okay, seems like no questions. Okay, no question, we stop here, okay? And I will see you again online tomorrow.
Okay, doctor.